right. Well, I hope you can hear me well. Good morning, everyone. Thank you very much for the introduction. Thank you very much for inviting me. Thank you to the organizers for giving me the opportunity to give this keynote. Very excited to be here. Very happy to see a lot of familiar faces. And I know if you're coming from the West Coast, this might be a little bit early for you. So thank you for being here early. All right, so before we get started, I would like to tell you a short story about how I started working on correctness in HPC. So when I started working at the lab, I was working on a debugging tool, and the debugging tool was supposed to catch correctness issues in MPI applications. So the tool was supposed to debug application hang. So as you know, when you use MPI, if you use MPI incorrectly, you can create a deadlock in the application. And so my tool was supposed to debug those hangs when they happen in the application. And when I started using, so I worked really hard on the tool, and when I started using the tool on applications that did not have a hang, my application actually, my tool actually created a hang on the application, a totally correct application. My tool was creating a problem. So my correctness tool had a correctness problem in it. And I spent a lot of time trying to debug that problem. I didn't have a tool, actually, that I could use to debug my tool, right? So that's when I realized how difficult it is for HPC developers to debug correctness problems, and how much time can be lost and how much productivity can be lost. And after that, I have been working at the lab for more than 10 years, and I work with the Compute Center to create new debugging tools and help them solve some of the correctness problems they see in the applications. And I wanted to start the presentation with an example of a real example of a common correctness issue that we see in the Compute Center. And I like this example because it shows some of the challenges that we see in the Compute Center, and some of the challenges that I think we should address in this workshop. And this happened about a year ago, so it was a scientist working on his code, and he was getting different numerical results. Right? So he was getting different numerical answers, even when he was using the same executable and input, but over different runs, he was getting different numerical results. And the problem started to happen when he moved the code. He ported the code to a new system that had GPUs. And he spent a lot of time trying to debug this problem. The problem manifested only in a few runs, so you would get this incorrect result only in a few runs. And so he would spend a lot of time trying to reproduce the problem so he could actually give us a reproducible, so we could actually help him as a support team. And so I like this example because I mean, it shows some of the challenges and some of the characteristics of correctness problems that we commonly see in the Compute Center, right? So the first characteristic or challenge is that this problem happened when he ported the code into a new system. In this case, he was using a GPU, but it's not uncommon to see correctness problems to happen when code is ported to a new system. The other challenge is that there is non-determinism here, and this really makes correctness problem really, really difficult to debug. And I'm going to give you more examples later. But non-determinism is a huge problem. And the other challenge or characteristic is that, well, there's a lot of time lost, right? So I'm going to go through more details on these characteristics of correctness problem, but I wanted to start with a real example of what are the things that we commonly see. But in this talk, I would like to answer a specific question. I would like to, which is the question I have in the title of my presentation. How can we help programmers focus on correctness before they even think about performance? I mean, performance is in the title of the domain, right? So high performance computing. But I think correctness is not usually the main concern for HPC developers. HPC developers are driven by many other things. They would like to run larger HPC workloads. They would like to run larger AI workloads. They would like to leverage accelerators, domain-specific hardware, right? And they would like to have performance portability because they are moving code from one system to another system. Or maybe they are running on the cloud and they want to take advantage of the hyperscalers, right? But correctness is not in front of the car, but I think it should be. It has to be, right? Because if they really want to spend less time debugging code, correctness should be one of the main things that they should think about. And maybe there's an opportunity for us in this community to help them maybe address or have less correctness issues in their code so they spend less time. They're more productive in what they're doing, right? And I'm going to try to answer that question at the end of the presentation. But during the presentation, I'm going to divide the talk into different areas. So first, I would like to talk about some of the challenges in HPC correctness that I think are important. And the reason I want to do that is that I know we have different people from different backgrounds in the room, right? And I'd like to make sure everyone is on the same page on the main problems that we have. Then I'm going to talk about some of the consequences of correctness issues that I have seen have impacted code teams. Some of them, I would say most of them, are on the area of productivity loss. Then in the third part, I'm going to show some ideas, some opportunities that I have, that I think we have as a community to have some community-wide impact. And then in the last part, I'm going to try to answer the question, how can we allow programmers to focus a little bit more on correctness? All right, so let's start with the first part. So here I would like to start with testing. So testing is I would say, is the standard practice for most scientific application teams to ensure correctness. People do a lot of testing, but as we know, testing cannot address all bugs, right? So first of all, we are dealing with a large number of inputs. We cannot test all the inputs. We are dealing with large arrays of floating point values. So it's impossible to address all the inputs. And the other thing is that in scientific computing, we don't have an oracle many times, right? We don't have a testing oracle that we can use to know what's the correct output of the application. I mean, the main reason we're running a science application is that we don't know the answer for that scientific simulation many times, and that's if we're dealing with a bank application, maybe for the bank application, we have all the states and possibly all the outputs, and we can use that for testing. But that's not the case many times for scientific computing applications. And so the reality is that this leads to a situation where we have bugs that are hidden, and those bugs later on manifest maybe for a given production run, maybe when people have to meet a milestone and they're running the whole system, this is where they get the bug, they get the correctness problem manifest itself. So we end up with a situation where we have input-dependent bugs and scale-dependent bugs, right? So we actually did a study a few years ago on 25 correctness issues that we saw at the lab. So these were 25 correctness problems that require extensive debugging. So what this means is that scientists tried to debug the problem, but they couldn't. And so they contacted us in the research center, in the compute center, to help them find where the correctness problem was coming from. So they spent a lot of time trying to find, to isolate the problem. And it's a combination of software and hardware issues. This was mostly done by Kento Sato when he was at the lab, and he's now at RIKEN. So we took these 25 cases and we classified them into 5 categories. So the categories will be determinism, scale dependence, termination. So termination meaning whether the problem terminates and gives us an answer, or does it hang or crash. The location of the problem, whether the problem is in the application, the system, or is external to the application, and the cost. So for the cost, we look at whether we had a specification violation or not. So for example, if you have a data race in OpenMP, that would be a specification violation. So we took those 25 cases, we classified them. Here's the table of the results. I hope you can see this table. I'm gonna share the slides later on so you can take a look at the data, but let me go through some of the columns here. So the first column is just the ID. The second column is whether the case is a non-deterministic or deterministic case. So ND means non-deterministic. And as you can see, there's a lot of ND cases, a lot of non-deterministic cases. Then we have scale dependence. So scale dependence means, is this correctness problem happening only when I run the code on a given number of processes or a given number of threads? That's scale dependence. Termination, that's the 4th column. You see a lot of hang cases, a lot of slowness, crash. Then we have the location, whether it's external, system-related, application-related. the cause, and then some description of the case. So for example, the first case was a hang that happened at about 1 million MPI processes in a given cluster. So there are some things we learned from that study. So the first thing is that 72% of the correctness issues were non-deterministic. And again, these are correctness problems that people try to debug, they couldn't, right? They spent a lot of time trying to find where the problem is. And 72% of those cases are non-deterministic. This means that as a community, if we can address that problem right there, the non-determinism, that will have a huge impact in the community. 64% of the cases were scale dependent. Again, another big problem where where correctness problems actually manifest themselves at large scale, right? Several cases involve libraries and runtime, so it's not uncommon to see, for example, the MPI library being involved in some of these cases where people use incorrectly MPI and so on. Data races and message races were not uncommon. You would think data race checking is a solved problem, right? But in practice, we still see a lot of data race cases, and sometimes we don't have the tools or the analysis that we can actually use in a data race case to find where the problem is. And the other thing we found is that debugging tools can be sometimes tricky to use and tricky to combine. Actually, when we have to deal with these large correctness problems, we have to combine debugging tools or correctness tools, but they are sometimes difficult to combine. When you use one tool, then that will interfere with the second one and so on, so it's very tricky. All right, so I have mentioned that testing is the standard practice, but I haven't said why is testing still not enough? Why is it so difficult to use testing to check for the correctness of applications? And clearly, I mean, it works, but still we have problems, right? I mean, many of the cases that I presented here are from applications that do a lot of testing, and I've seen those tests, but still they have correctness problems, right? So why is testing so challenging and so difficult? And I would like to use the notion of the approximation tower from Konrad Hinsen. That, I mean, he presented a paper, he wrote an article about this notion. And I like this idea to explain why testing is so difficult. And so the notion is that as we move from physical reality to numbers in a simulation, we have to apply a number of layers. And many of these layers, so we have physics layer, numerical analysis layers, and software. And many of these layers, actually all of those layers, perform a good number of approximations. And those approximations is what makes testing so difficult. So let's start with an example. Let's say we want to model, we want to have a simulation of the solar system, and we'd like to have a numerical solution of the solar system. That's the first layer, right, the physical reality. Then we go into the physics layer where we do a good number of approximations, right? So we could do, for example, we could include all planets and the sun, but we don't include the moons and the smaller bodies like comets. We may say, okay, we don't include the galaxies because they are so far away. We reduce each celestial body to a point mass. And that's a reasonable assumption because, you know, the diameter of the planet is significantly smaller than the distance of the planet to another planet. So that's a reasonable approximation. We keep doing we may apply Newton's laws, but we know they approximate Einstein's theory and so on. So we do a good number of approximations in that layer. Then we go into the numerical analysis layer where we do more approximations, right? So differential equations are discretized into finite difference equations. Continuous time now will take discrete values and so on. And so here numerical analysts can actually make general statements of stability. But we know that for large problems, realistic, very large problems, that's very difficult. For small problems, it's relatively easy, but for large problems, it's hard. And one of the reasons that we have floating point here, we have in that layer, we are using IEEE floating point arithmetic that introduces rounding error. Rounding can be, you know, error can be propagated to many layers in the software stack. And so we know as a community that it's very difficult to estimate the impact of floating point in practice, right? And then we go into the last layer, the software layer, where I think most of the problems are coming from. And in that layer, what we're doing is a number of program transformations for performance, mostly. So we do things like parallelization. We take a serial program, make it parallel. We do program transformations by, you know, sometimes it's done manually. Like, for example, we are porting a code to use a given interface. But I think that the most important challenge here is the third approximation, which is compiler optimizations. So the issue with compiler optimizations here is that they can change the code drastically, and this basically creates a situation where you can have numerical computations that are different between two computers. Or even the same computer, if you're using two different compilers, you might get different numerical results. Even in the same compiler, if you're using different optimizations, you might get different results. So that's a huge challenge for testing and for reproducibility. And another problem is that we have, the programming languages, at least the programming languages we use in HPC, don't specify clearly what the result of floating point expressions should be. And that's another limitation that we have for testing. So having said that, we have made good progress, actually, in the recent years on the issues of compiler-induced numerical inconsistencies. So some of us have worked in this area. And the way we define the problem is that if given an application that produces different numerical results, because the application was compiled by two different compilers or two different compiler optimizations, we would like to know, or the developer would like to know, where in the code the problem is coming from. And we have actually developed a good number of tools, and we have done research in this area to find where in the program the problem is coming from at different granularities. So we started with Fleet that can analyze CPU code, and it can find the function that causes the reproducibility problem, the inconsistency. Then we have P-Liner that can do the CPU analysis as well in a code, and can find the line of code that caused the problem, that caused the inconsistency. And then recently we had Seal that can find actually the expression within that line that caused the problem. And we just presented that paper recently at ISC. So we have made good progress there, but I think we can do better. And here are some ideas, maybe wild ideas of things that we could do better in that area. So the first one will be, what about we allow programmers specify the exact order of floating point operations? Because right now the compiler transformations are out of control, but that, I guess the problem here will be, how do we do that and still get good performance, right? Because I mean, the reason we're doing the optimizations is that we want performance, right? So compiler optimizations are the first line of tools that people use to get performance. So how do we do it? We want to remove the diffuseness around floating point arithmetic, and this is where floating point education is crucial. And I invite you to read Peter Dinda's paper on Do Developers Understand IEEE Floating Point, where you would see how some people actually don't understand all the details of floating point, and that can be, that can have some impact in testing and ensuring correctness. What about embracing other numerical formats in HPC? So I mean, right now, floating point is not very friendly for to verify correctness. So the community may actually adopt other formats, which actually can help us to verify correctness better. What about envisioning testing methodologies that are driven by machine learning? And so, we don't have an oracle, as I said before, but we could use some models that would allow us to maybe get some expectation of the test outputs, right? And the last idea would be generative models to generate test cases. So what about using some way to generate different classes of tests that could find failures in programs? And I know this idea works because we have done some work on automatically generating random tests. So here's an example of a tool that we built that can generate random tests, and we did this for finding compiler inconsistencies. Compiler-induced inconsistencies. This is a random test. You don't have to understand the code because it's randomly generated. But we find cases like this where if you compile this code, this random test, and you run it with an input, you compile it with two different compiler and two different optimizations, well, the same optimizations in two different compilers. You run it on the CPU and then you run it on the GPU. You get different results, totally different results, by running your code in the CPU and then running it in the GPU. So we find cases like this just by randomly generating tests. Imagine what we could do with more advanced generative modeling, right? So I would like to say something about formal methods. So for many years, I have tried to convince people to use formal methods more to complement testing, right? And the reason is that, well, so there has been a lot of advances in formal methods. right? So from specifications to a lot of proof assistant tools. There are several applications at scale in industry of formal methods. But I have found a lot of resistance from code teams. So they, you know, the main arguments for not using formal methods is that it involves too much mathematics, takes too much time to use, and you know, they see little value, they perceive little value from formal methods. But I have to say that formal methods have a role to play in HPC. Actually, we have used formal methods, and I want to give you an example for verifying some code that we actually run in the clusters. So we have used formal methods before to verify the correctness of fault tolerance in the OpenMPI library. So we have implemented a fault tolerance algorithm, the RENID algorithm, in the OpenMPI library, which is widely used. This was actually funded by ECP, this work. And we use TLA+, which is a model checking framework. And we use it to verify the fault tolerance algorithm in the library. So we verify, for example, that when a failure happens, all the processes recover from the failure, and they all reach a certain point in the program. And we have also verified that there are no deadlocks in the recovery algorithm. So we have used formal methods there, and I think there is as I said, formal methods have a role to play, and I'm looking forward actually to the second keynote that is going to talk about formal verification in scientific computing. All right, so let's now, I'm going to give you some consequences of correctness issues that I have seen have impacted the productivity of people. So this one you probably have seen before. We have used this in a number of papers. So this was a case that happened when a group of people were developing a hydrodynamics mini application, and they were porting this code into a new system. It was an early development. The new system was an IBM Power 8 with NVIDIA GPUs. And so when they compile the code and run it with different optimization levels, they would get different numerical results for a specific compiler and a specific compiler optimization level. So that would be the XLC compiler with -03 optimization level. And so they would get a very different energy value. And developers know that when you use compiler optimizations, you might get different results, right? People know that. But usually those differences are in the last digits, right? Usually they're in the last digits. But this one is actually in the second digits. It's a huge difference. And the code team approached us. We tried to help them. It took a lot of time to debug this problem, several weeks of effort. We tried many things. We tried delta debugging, to analyzing the assembly, using debuggers, and so on. So this consumed a lot of time. So that's one example of productivity loss there. This is another interesting case. So this was an application that hung intermittently at MPI functions, right? So the problem occurred after a few hours of execution. So you would think that, you know, this is something that also consumes a lot of time, because if the correctness problems happens only after a few hours, right, let's say you have to run the code for 3 or 4 hours, and it's an intermittent problem, I mean, you have to submit a lot of jobs to actually be able to reproduce the problem, and that's what happened actually. So because it was non-deterministic, the scientists had to submit many identical jobs to reproduce the problem and be able to give us a reproducible, because it only manifested in a fraction of runs. And so what we found, the debugging team found that the problem was an MPI message race. And so basically they were using identical MPI tags in a non-deterministic set of communications. Basically they had two groups of processes communicating to another process. And to differentiate between these two communications, they should have used different MPI tags, but they were using the same tag. So in total, the application developers spent 2 months, it was a 2 months effort, over an 18-month period, and that was before giving up. That was before trying to debug the problem by themselves, and then giving up, and then contacting the support team. And even when we took the case, it actually took several weeks to find where the problem was. So that's a good case of productivity loss. And the last area I wanted to mention is hardware errors. So sometimes hardware errors can take time to isolate. Rarely we see processors that can cause correctness issues. It's not common, but I mean, we see cases like that where we have bad hardware producing incorrect results. And this could be because the processor is aging, or we just have to replace the processor. But the process to finding what node in a large cluster, what node the problem is coming from, can be tedious. So we have to submit several jobs and then do some sort of bisection search. And even when we find the node that had the problem, we still have to run a lot of tests in that node before we give the node to the vendor, right? Because we need to get a replacement. We need to give that to the vendor. But before we do that, we actually have to make sure the problem is coming from that processor. So those cases, not common, but I would say can take a lot of time to isolate as well. All right, so now I would like to talk about some opportunities that we have and some provoking ideas to have some community-wide impact. So the first opportunity is helping programmers verify the correctness as they integrate surrogate models and machine learning models in scientific applications. And there are several code teams that are trying to do this today. So the idea is that, and the AI for Science report has several examples of how we can replace a part of a simulation with a surrogate model. There are many applications that could benefit from this, from plasma physics to particle transport and so on. And so the idea is to replace part of the simulation with a surrogate model, right? And so we could use experimental data to build the model and maybe reuse the models across simulations. So that's the main idea. And there are several teams trying to do that. We have a few groups in Livermore that are trying to do that. But they are actually facing correctness challenges here. So one of the challenges is that when they integrate the machine learning model into the code, the error can build up quickly. And then the simulation ends up doing more refinements because it needs to simulate in more detail for that particular part of the code. And then the simulation takes more time, takes too much time, and that defeats the purpose, right? Because we want to add the surrogate model to actually accelerate the application. And I have to say that the tools that they use to debug these correctness problems are manual, right? So they have to use visualization-based tools and things like that. So this is where I think correctness checking, having models of correctness could actually help them better estimate the error. But I would say most applications don't have those correctness models that they can use. Maybe having assertions in the code that can detect the error early on, because the error propagates quickly when they integrate the machine learning model. So that's an opportunity I think we can have right now to help those code teams in the area of correctness. Another opportunity is helping people to verify the correctness as they use different numerical formats. So this graph shows the increase of numerical formats in NVIDIA GPUs. So as you know, NVIDIA GPUs are widely used. And they started with FP32 format a long time ago because the market was dominated by 32-bit video games and things like that. But the number of formats has been increasing recently, and we have now, I think, at least 6 formats in an NVIDIA GPU. And so we have an opportunity here to help them verify correctness as they use mixed precision or as they integrate some of those formats in their code. There's an opportunity as well on compression methods, right? So compression is widely used as well in HPC, and as we do compression on different formats, there's an opportunity there to help them verify correctness. All right, so now I would like to give some provoking ideas, some long-term community-wide impact projects that I have, and feel free to disagree with me. If you have other opinions, they are welcome. If you have more ideas, they are welcome as well. I would like to just start a conversation in the workshop with these ideas. So the first one would be compiler optimizations guarantees. So and this may be crazy idea sometimes because I know this is hard to do. But if we have more guarantees, better guarantees for the optimization. So for example, if we can inform the error, how the error is introduced, that would be great. Because right now, scientists see the compiler as a black box, pretty much. They don't know what's going on. They don't know how the code is optimized. And if we can control optimizations from the program, that would be great as well. We have some control, but we don't have a lot. I would say in the open source compilers, there's no too much control. So the second area would be verification of runtimes and libraries. So if we can take a code that is commonly used in applications like libraries, for example, math libraries or CUDA runtimes, OpenMP, MPI runtimes, that would have a lot of impact because these are runtimes and application and libraries that are widely used in applications, right? So if we can verify different logic aspects of those runtimes, like we did, for example, for the OpenMPI library, where we just verify an algorithm, and we know that part works really well. That would have a lot of impact in applications. Correctness checking as we type, so more advanced IDE checking, and I know there has been a lot of advances on IDE checking, right? Even in the machine learning area, with ChatGPT and all of these things, you can write code and it could tell you, what is wrong with the code. But I think the challenge here is to, it has to consider parallel code, and it has to consider numerical software. And I think most of the advances are not considering that. So that's an opportunity for us to have some impact there. Improving the scalability of dynamic analysis. This is another crucial area. We do build, as a community, we build a lot of dynamic analysis tools. But if a tool is going to take 100x, I mean, the scientists are not going to even try, right? Because if they have to run a code for several hours and run something that's going to do 100x slowdown, they're not going to use it. And I think there's an opportunity in the research domain where we could understand better what code has to be instrumented by that tool and what other code doesn't have to be instrumented, because we can maybe regenerate the inputs for that area, or I don't know how to do it. But if we can understand better how to improve the slowdown of many dynamic analysis tools, people actually will start using more of the tools that we develop. And the last one is more tools for formal methods. So the idea is to have more tools that allow formal methods to be more usable, more easy to integrate in the programming models that we use. So I think that will be another area. All right, I'm almost getting into the end of my presentation, and I would like to bring up the correctness workshop that we organize. We have been co-organizing this for many years. I co-organized this with Cindy Rubio Gonzalez, my collaborator from UC Davis. We have run this for 6 years. This is year number 7. I think there is something to learn from this workshop, from the papers that have been published and the ideas that are there. We have built a community around the correctness in scientific computing. There's a good participation from international groups. I mean, we have people coming internationally every year to this workshop. And these are some of the most popular topics in the workshop. And this year we have a special event. Actually, we have the HPC Bug Fest. And so the idea is to gather buggy codes that we can use actually to compare or evaluate tools, right? So let's get a bunch of buggy examples that we can use, because we don't have a lot of them. And we can use them to actually compare tools and evaluate different classes of verification tools. And this particular event in the workshop is chaired by Emmanuel Sailar in INRIA. All right, so now I would like to answer the question, and this will be my last slide. So how can we help programmers focus more on correctness, right? Maybe they're not going to focus on correctness first. Maybe they are still going to think about performance. But how can we help them think about correctness a little bit more so they can spend less time debugging code? So the first thing is formal methods must become standard practice. And for that, I think we need more tools. And the reason I said that is I just saw a podcast from the ACM that was talking about correctness by construction. And the speaker was saying actually how by building more tools, people can start actually using more correctness by construction. So I think this is an area where we could make improvements, so we can use more formal methods in our codes. Correctness tools must be easy to use and easy to integrate. If they're not easy to use and easy to integrate in the workflows that people have, and the applications that we deal with have very complex workflows, and if tools are not easy to integrate in those workflows, it's very hard, right, to use those tools. Correctness methods should be part of a standard practice in HPC. I believe that, and the standard practice, as I said, is testing. So, we should think about how we can help them do better in testing in general. And we have opportunities in the CI area where we can actually check for correctness as we push code into GitHub. And we should address the reproducibility and non-determinism problem. As I said before, these are crucial things to address because these are the aspects that actually make really, really difficult to find and debug correctness problems. So let's address that. And the last thing I have to say is that we must show value to users. And the way to show value to users is reduction of time to solution. That's really the way. I mean, really the users of scientific applications, they don't really care much about details, computer science details and formal method details. What they really, really care about is results. They really care about scientific results. If they can have more scientific results, they will be happy. Right? If we can help them have a higher rate of scientific results and help them do more science, that will be the way we can actually impact their lives. And with that, I'm done with my presentation. Thank you very much, everyone, and welcome to the workshop. I'm happy to take any questions. I think it's time for some questions.
Hello?
Very disturbing about the table you presented on slide 8, which is, the 25 examples where people sent you hard bugs, which is almost every single one of them is a termination bug. It crashes or hangs, which is obvious to anyone that there's a bug in the program. And so that means that in all the other 1,000 applications, either it terminates with quite accurate results, or the results are completely inaccurate, but nobody has any idea. And that's what's disturbing about this table. There are no bugs on this table of the results inaccurate. It's all crashes and hangs.
Good point. Yeah. There are a lot of hangs. There are a lot of hangs, I have to say. Many of the problems we see are when the application hangs at large scale. You have thousands of processes running. What do you do about that? Right? So that's. Oh, about accuracy. Well, except the examples that I gave where we have the incorrect. So yeah, we didn't include that one here. Yeah.
So there could be a valid reason for this queue. You don't send a bug to a person who's not embedded in the project when it is an accuracy bug, because you don't expect them to be able to reason about why that is happening.
Well, I have to say, I don't know if you were here in the beginning of the talk, but I gave an example of a problem with an incorrect result. That was sent to us. He was getting different numerical results when he was running the code on a GPU, and for different runs he was getting different numerical results. He didn't know why. He spent a lot of time trying to find where the problem was coming. And if you are interested, I can tell you what the reason was, but he spent a lot of time on that.
Yes. So last question on non-determinism. So you mentioned this several times. What is your definition of non-determinism? And is it just the fact that the execution is not deterministic? Is that the result is not deterministic? How a non-deterministic result actually affects the analysis and the science? Because you may have some small deviation at the end of the representation, and that might not change the result.
Yeah, so the way we define non-determinism was based on the correctness problem being manifested. So the manifestation of the problem could be either the program gives an incorrect result, it crashes, or it hangs, or it terminates sometimes well. So the non-deterministic means the manifestation, let's say it's a hang, would happen. It doesn't happen in every run. Execution, exactly. Yeah.
Hi, thanks for your talk. So coming back to Andrew's point a little bit, so I think you showed us a lot of bugs that you know about that are hangs or which are obvious bugs. Then there is also like a bug that is basically depending on the optimization level, you get different results. So it's because you get those different results, then it's obvious that you also have a problem, right, of accuracy. How many problems do you have that do you think there is that go completely undetected, Because at every optimization level, I get the same result. This result happens to be wrong, but nobody knows, right?
Right.
It's like, I mean, do you think there are lots of them? I mean, do you just have no idea?
Yeah,
Do we have no idea?
That's a good question. I mean, I have to say I don't know, because that will be an undetected problem, and it's hard to say how many of those undetected problems are there if we don't have a way to detect them. All we know, I work on a support team with Livermore Computing, and we get those really difficult to debug cases, but they can still have those problems there where they don't even report those cases to us. And I show you an example where they spend 18 months overall trying to find a problem. Maybe they have those problems there, they don't, they spend a lot of time there, they don't tell us, and there could be a huge productivity impact for them there. But yeah, I mean, for things that are undetected, it's hard to say. But I would agree with you, there are possibly a good number of those cases. Yeah.
We'll take one. Thank you. We'll take one last question from Laura.
Okay.
Hi, Ignacio. When you talked about checking correctness while we type, are you envisioning embedding in IDE like a testing or also formal methods tools?
I would say both of them. Testing, and if we can embed some of the formal methods, techniques that we have. Assuming we have some way to specify what I'm going to be writing, I guess that would be the way to do it. I don't know exactly how to do it. But the idea would be that we check for these problems before they are hidden, and then they impact their code later on, where they are running at at a given cluster or at large scale. That would be the idea.